now I'm going to talk about a very important topic, which is about training and hosting models, large language models using Amazon Sagemaker and some of the libraries for doing this distributed training, right? So first and foremost, why do you need distributed training for large language models? As you guys can see in this slide deck, there is a rate. We are seeing the compute increasing, the requirements increasing, and one of the things that we notice is that hardware is getting better, but much more we are seeing a much higher increase in the numbers of requirements to train some of these large language models. And we, of course, we can notice that the pace we have with hardware will not catch up with the requirements for the large language models. And that's why we need to follow or to use this distributed training approach, right? So just as a recap, basically we have data parallelism and also model parallelism, right? So just to remember, when you have data parallelism, the training data set is split across multiple nodes, and each node has a replica of the model. And then each node performs a forward and backward pass and synchronizes the gradients between all the nodes, right? On the other side, what we have is that when it comes to model parallelism, we have a model which is partitioned across, which is split across multiple nodes. And usually we do that when we have larger models, right? Just as a recap, there are many kinds of distributed training, right? So when it comes to distributed training, other than data parallelism and model parallelism, we have job parallelism. And specifically to model parallelism, we have some different flavors, if you will, which allows us to make the most, to train those large language models, right? For example, when we use model parallel approach, when a large model doesn't feed into a node's memory in one piece. So basically we need to break up the model and place different parts in different nodes. And in this situation, what happens is that we need to send batches of data out to each node so that the data is processed on all parts of the model. So that is what happens, right? And what is the use case for model parallelism, right? So just as a recap, of course, when we run out of memory, this is a use case. And also we use this when we need to maximize GPU training. And in other words, a common pitfall we see when we are splitting layers across devices is severe GPU underutilization, right? And that's where the Sagemaker parallel libraries comes into play, because it includes things like automatic model splitting, and you utilize some of the techniques that I'm going to talk about in the next few slides, which helps us to make the most of these procedures. For example, when it comes to model parallelism, you're going to find that we have model parallel software that shards tensors or layers of models onto GPUs, and basically it handles the learning loop, including forward and backward passes, right? So this is one of the key things we do. Model parallelism at the basic level concept. But then if you want to do something more sophisticated, for example, in this picture, you're going to find that we have GPU 1, 2, and 3, right? And then layer 1 and 4 are processed by GPU 1, layer 3 by GPU 2, layer 2 and 5 by GPU 3, right? This is a common way to tackle this. However, if you wanted to do this at scale, we need that third type of distribution that I talked about, which is a tensor parallelism, which basically applies the same concept of model parallelism, but they break apart the largest layer of the neural network and place those parts of the layers themselves on different devices, right? So this is relevant when you are working with models with hundreds of billions of parameters or more and try to fit even a few records into RAN along with parts of your model to train that transformer. So for example, with this approach, you can train a GPT-3 size model on Sagemaker. And this is what there is a blog post that I'm going to share with you, but this is what has been achieved. Like with this approach and using a P4D 24 extra large instances, 120, we managed to process 32 samples per second. And if we are able to double this, we are able to train a GPT-3 model end-to-end in just 25 days, which is almost which is around 4 times faster than using the P4D 24 extra large instances, right? So in other words, using this approach with tensor parallelism, we are able to train these large language models because we can spread a single layer across multiple GPUs, and this is done under covers. You don't need to do this from scratch, but basically you need to make some parameter changes while setting up your training process. I'm gonna speak about that. This is pretty much a summary of what I just talking about. We have pipeline parallelism, tensor parallelism, and share their data parallel, right? Which is pretty much where we have all GPUs split into partition groups, where a group holds a full copy of the model within the group, and then those parameters are sharded between the GPUs. That's a way to manage this, right? And on top of that, you may combine with some memory optimizations like activation checkpoints, offloading, optimizer state sharding, and things like that to train your model. So whatever you're trying to do with these large language models, like running them or fine-tune them or customize them or training from the scratch, you're going to need to leverage some of the infrastructure, like to train your model, to host your model, like using endpoints. And basically, we have created over the last 5 years, we haven't been investing on these purpose-built accelerators for generative AI, like the inference and training, which has achieved some great benchmarks and important results when it comes to training speed, as well as improving power consumption, and also lower cost, the overall cost training. For example, for this, in this picture, there is a benchmark where we used training to train a BERT model, which is not as big as the ones we have at this point. But what we achieve is that we managed to reduce the training time by up to 2.6 times. and then we managed to do this 2.6 times faster and with 52% less energy. So these are some of the benefits of using some of the techniques that I talked about, like distributed training, using, for example, model parallelism with tensor parallelism. And then on top of that, leverage some of this infrastructure to go to take this training process to the next level. And also, speaking about large language models, we have the training portion as well as hosting a model, some of these large language models. And of course, there are some of the things we need to consider, right? So whenever you need to deploy these models into production, you need to have an inference or an endpoint from the model for your applications to consume, right? But you need to think about three things, right? Before one of the things is the first is complexity of the model that you want to deploy. For example, one way complexity can manifest is the size of the model. You probably have seen in the previous sessions where we spoke about like the Flame, T5, Cohere, Jurassic T2. You probably have seen the Bloom, and there are different number of parameters as well as number of tokens and things like that. So you need to consider that the dimension and the size of the payload you're going to send to that inference point. This is one thing that you need to consider. And also the second factor that you need to take into account is the performance itself. For example, one of the key areas you need to consider is to do some prompt engineering where you're going to be teaching the model and provide additional context for the model to answer with more accuracy and more precision, right? And we need to have an answer which is as fast as the application, or for example, let's say I'm building a chat for the Q&A and I need the answer so fast. So, and imagine that you're gonna need to serve millions of transactions per second with a high throughput, and this is one additional thing. And also, of course, the third factor is that we need to think about cost. And when it comes to cost for inference, whenever you are, for example, deploying a model, as you have seen in the previous exercise, you're going to need an endpoint or a host to serve for inference, right? This is a key thing you need to consider. And also, when you are doing some fine tuning, you're going to need to run, you're going to need to train, you're going to need to provide some additional data to be trained against this pre-trained data set. And that will require a training of a few hours eventually, or from minutes to hours. And then you're going to need to serve for inference. So these are the key things to consider. When it comes to model size, let's say we are going to pick up the GPT-J, which is a 6 billion parameters. And taking a quick look into the memory requirements to load this model, you need to think about training for loading this model. You need to see from two different perspectives, right? One is the training, and the second one is the model serving. For example, for this one, for the FP32, you require around 24 gigabytes to load the parameters, and then the same for gradients, and the same thing for squared gradients and optimizer states and things, and some activation memory footprint plus batch size, which accounts for 200 gigabytes, more than 200 gigabytes for training. And when it comes to model serving, to load this GPT-J in float 32, you're gonna need at least two times model size CPU RAM, one for initial weights and another one for the checkpoint. So with this, you're gonna see that we have all of these requirements for training the model and also for model serving. So what are the techniques and what are the things you need to consider for optimizing models for hosting with Amazon SageMaker? So basically, here is a very high level overview of the most of the model inference optimization techniques and we can use. For example, just as a reminder, optimization can happen at both the hardware level and the software level. But in this, we are going to only focus on the software techniques because the hard technique has been applied, for example, to the training and inference instance, right? So the first thing we need to consider is the model compilation. For example, things like operation fusion or constraint folding. So basically, this approach results in better performance without compromise the accuracy of the model. This is something that we need to use. For example, during the demo, you're gonna learn how to use deep speed or for example, for model compilation. This is one of the things that we can do. Also, we have deep speed for model compression, which is an approach to make easy to compress models for researchers while delivering faster speed and a smaller model size. The downside of this approach is that we are decreasing accuracy in favor of best performance and a smaller model, right? So sometimes we need to combine some of these techniques we have available through SageMaker to try to find a sweet spot. But these are the things we can use, right? And also we have quantization, which involves, for example, transforming a model into an equivalent representation that use parameters and computations at a lower precision. So, for example, I can go from FP32 to FP16 to the low bit ones, right? Or like int1 and int4. So we are gonna lose in accuracy, but we're gonna reduce the time taking to serve inference by having a smaller model, right? And one additional technique is about model partitioning, and of course, as you learned, you may combine prompt engineering, which is post-hosting, right? So please note that all of these techniques that I just talked about some of them are post-training, and some of them are during runtime where I use where I configure some of the parameters with deep speed, for example, using a mix of these three techniques under model compression with deep speed. And also we have model partition, which is an option, and prompt engineering to finish. When it comes to hosting an optimization pipeline, this is pretty much the overall process as I just described it, right? So we have the model optimization, which is in training or post-training. Then when it comes to model hosting, we're going to use deep Java library, but for all these three steps, right? And then post-hosting using prompt engineering. So these are the key things. But even though the name says Java, it doesn't have anything to do with Java itself. You can use with whatever language. We don't have any limits for that, just so you know, right? And for having this large model inference, we have created the LMI container, which are used, which is one of the models we use to support this model with billions of parameters and a massive amount of data. And this is the model we use within Sagemaker, right? And basically, we are able to leverage deep speed, stable diffusion, and Hugging Face handler to optimize the way we serve models, right? This is and for example, we have optimized kernels for popular models such as OPT, GPT, and Bloom using this LMI container, which is available within Sagemaker. And let's dive deeper into one of our solutions for serving a GPT J6 billion, right? In this case, as you know, as you probably have heard, it requires at least 24 gigabytes for FP32 model, right, with initial weights. So this is what the solution looks like, right? So we have Sagemaker with this LMI container, which includes deep Java learning, serving, inference, and model parallelism, which is included within this container, right? So includes the deep speed inference, the model tensor parallelism, and the deep Java learning within this container, right? So what are the benefits? So basically, you can host any types of large models using this model partitioning, and it has some sharding techniques across multiple GPUs. So basically, you need to set up a properties file where you're going to need to, where you can, you're going to take advantage of this model parallelism that I just described. You don't need to do something from scratch. For example, with this LMI, you are able to have faster model downloads from S3. It supports also BF16 with deep speed, and support also some of the key models like deep speed, Hugging Face, accelerated, and stable diffusion. So this is only an example of some of the benchmarks we achieved by training the same BERT model. We required 50% fewer instances, less energy, and lower cost to train to serve a model using these techniques provided out of the box by the LMI container on top of Inferentia 2. And basically, this is important to know because sometimes you may need to train a model from scratch, or even when you are fine-tuning, you're going to use the DJL with deep speed for fine-tuning. And by the way, this is one of the things that I'm going to talk about. Let's jump to the demo so I can explain what the large language model hosting on Sagemaker looks like with Hugging Face, accelerated, and also deep speed. Let me go to my console over here, right? Okay, so basically this is in this Jupyter notebook, I have a large language model hosting on Sagemaker using deep speed container as well as Hugging Face accelerated. So the process is really straightforward. So you create a Sagemaker model for deployment. You need to import a few libraries, right? Then we are doing this for the GPT J6 billion, right? As you can see here, this is the model prefix we are using. I'm setting up a region account and connecting to S3 and the Sagemaker as well. And this is the inference image we are going to use to do a distributed training. In this particular exercise, if you go through, even though you find this is only for a single GPU, if you, for example, come here and to this configuration file, and then you move for a server which has, for example, for all GPUs, basically need to set up this parallel degree, which is going to use all the GPUs to serve inference, right? So this is a way to do that. And also you can optimize different things like this is a task, text generation task, or a text summarization and things like that. You can just set up this deep speed source, and you can do the same for the accelerate source, right? So let me zoom in so you guys can see what it looks like, right? And this is the way we can set up. So going back to model, this is the one we are going to use. And then basically downloading the model, looking up the S3 model location. And then the next step is to deploy a large language model using Hugging Face accelerated. And if you look at this description, for example, you're going to see this is for text generation, but I may change and say, hey, I'm going to serve model for question and answering, or for example, let's say I do some task classification. Basically, I need to change this parameter and redeploy my model, right? We have more details on what the process look like, but here you're going to find some of the parameters, serving properties I used, right, within this container I just spoke about, the LMI. And you can point to these parameters by setting up the S3 URL, which is the location of the model files. Basically, you can say how many layers you're going to use, and if you're going to be supporting 8-bit or not. And this is pretty much a representation on what the process will look like. For example, you have in this example, you have 4 layers, right? And then I'm going to use different GPUs to serve model for each of these layers, right? And then once I'm done, basically I need to deploy my model. This is a function to deploy my model, which takes some minutes to complete. And once this is finished, I can use the predictor to predict a couple of things using GPT. For example, this is a simple one where I provide some prompt engineering, like a few prompt short learning. For example, support has been terrible for 2 weeks, sentiment negative, and so on and so forth. And this is the answer I got. So, for example, the responsiveness of your team has been amazing. Thank you so much. The sentiment is, of course, is positive. This is a model that I trained using Hugging Face Accelerate, which is a framework we can tune by using the LMI container with Sagemaker, which is which can allow you to train these against multiple GPUs. And also, if you want to do something different, for example, you can set up basically the same parameters like the process we are using. And this is another example using deep speed, right? The process is pretty much the same, right? And then, but what happens is that with this deep speed, as you can see here, we have multiple layers, and a portion of this layer is trained against GPU, and then we consolidate the result on each GPU, and then all of these results are collected through an all-gather operation to compute the final result. Right. So this is a different approach, and you don't need to reinvent the wheel. You don't need to start from scratch. Basically, you need to point to the LMI instance, right? The large model inference container, and that's it. Basically, you need to set up parameters, and you're good to go. And this is a way for you, if you wanted to get started with training your own GPT model and server inference. This is a notebook that I definitely recommend to you. But going back to the session, I just this is the first portion of the demo, but I wanted to spend some time with you. I'm sorry. To explain some of the tuning strategy. I know you guys have seen some of them in the previous sections, but I wanted to do a recap because I wanted to walk you guys through on what the process looked like to do fine tuning for a GPT-J 6 billion parameters. So in that case, I'm going to provide some additional data sets on the financial service context domain. And then I'm going to train this, I'm going to fine tune this model to be able to provide additional answers and more context and more background for a specific domain, which is around financial service. So we are using the Sagemaker Python SDK for financial services using the deep speed container, which I just walked you guys through so that you can make the most of this. But just as a recap, so we have prompt engineering, which is something that we do during inference, but we have prompt-based learning, which is a technique related to prompt engineering. But I say this one is a broader terminology because you do this during the training time, and you specify the method of training a large language model using prompts that provide domain knowledge and task information during the pre-training phase. So in other words, you can use prompt-based learning not only during while you are serving inference, but you can do the same, apply the same technique during training, right? So this is something to consider. And why business need fine-tune large language models? So as I was just saying, sometimes you need to customize to tailor the model to specific business objectives. So let's say training my model for the healthcare industry, and I wanted to provide some additional context for a model to be able to interact with a patient with medical records, for example, and being able to provide more language and have specific vocabulary on this domain. So this is a way to do that by using fine tuning. So this means you don't need to start training a 175 billion parameters from scratch, but instead, you basically need to provide a sample of data set, which just is trained against a small labeled corpus of data, which I'm going to show you in the next few minutes. This is a way to do that. So sometimes we see the concept of domain adaptation For example, we have the GPT-J 6 billion, which I'm going to show you. And this is applicable when data is labeled, and tuning is not task specific. So for example, I can ask a question, I can have a problem like, what are the key elements of a contract? So the original model will answer like in the first column, and a model that has been adapted to a legal domain will provide additional context and more precise and more accurate answer. And these are the ways we can train a model. We can use this using the Sagemaker Studio and also via SDK. And the same thing is valid when you wanted to do some task-specific task-to-task fine-tuning. For example, you have seen the Flan T5, Flan base, large, and different size. So this model has been tuned for a particular task. So that's why they have these different flavors of Flan, right? And then, for example, you may have a natural language processing task like sentiment analysis, which you have a prompt to, for example, determine the sentiment of this sentence. So I absolutely love this new restaurant, and the completion is positive. So we have task specific. So the model architecture is unchanged, and we can combine this with some prompt engineering. For example, in this example that I'm going to show you, I'm going to use the Jumpstart with deep learning containers and the deep speed and library to fine tune this model. So basically, as a reminder, this deep speed libraries was designed to reduce compute power and memory to train these large distributed models, right, with better parallelism. And you're going to see that I'm going to provide a data set with information from SEC filings from Amazon, which was based on this blog post, right? So basically, the purpose of this is to ask a few questions like, what drives sales growth at Amazon? Or what, for example, this is a sample answer. Amazon is the world's largest online retailer and blah, blah, blah. But with the fine tuning, the response is sales growth at Amazon is driven primarily by increased customer usage, including increased selection, lower prices, and increased convenience, right? So where this additional context is coming from? So we have this SEC filing data set, which is public available, and we have downloaded these annual reports, which Amazon provides to all the to all the investors, and we have downloaded and we have provided some additional context and train this GPT-J 6 billion to be able to provide these answers. So I'm going to this model domain specific at that fine tuning. You guys can see on the left side, this is the training. This is exactly the report that I downloaded from this public repository. You're going to see that there are so many things. This is a Form 8K, as well as many information. All of this is public. So if you wanted to give it a try yourself, it's feel free to do so. So you're going to see this is a basically taxi file, which I used in this example to provide additional context. For example, income from operations, interest, expense, and income, and things like that. So basically, going back to this example, it starts by setting up the model, right? It's setting up the environment, as you guys can see here. select the text generation model, which is the GPT-J 6 billion. So this is the model and version. And then it starts by running inference on the pre-trained model, the vanilla model without fine tuning. This is a very straightforward process. I won't spend some time over here. But what I wanted to show you is that here we're going to query endpoint and parse response, as you guys can see here. And this is exactly the same as you guys can see in the this table, which summarizes. So the question basically is this. This Form 10K report shows that this is the answer, right? And this is exactly the answer I received when I trained this model, right? Exactly the same. So it's a long answer. So let me scroll down. And this is using the vanilla model. Then what I did was basically to clean up the endpoint and I started a fine tune using the pre-trained model using the custom data set. As you guys can see here, the input could be either CSV or JSON or text file, right? And this is a sample of this training data set that I just showed. And basically, what I'm going to do here is that I'm using I'm going to pick up a training instance because that's not going to be an end-to-end training, but I'll need to do this fine-tuning with this training instance, right? And then I'm going to use the pre-trained model, setting the training parameters, which are here below, the training data set, the validation data set, and things like that. And then the hyperparameters, how many epochs, and learning rate, and things like that. And I can combine with some of the HPO for automatic model tuning, just in case. I can use the hyperparameter tuner provided by Sagemaker. And then using that data set, I using the transfer learning. I do some transfer learning. Basically, this is a transfer learning process. And this model is going to be trained using the existing one and combined with this data set. This takes some time. I'm going to scroll down because this one took me almost an hour to complete this. This is the model that I used. Let me scroll down. And then I upload the generated training model to S3. I can see the training performance metrics from here. And then I can basically deploy and run inference on the fine-tuned model, right? So this is where I'm going to use to train my model. A G5 24 extra large could be 12x. And then the same thing, I just deployed in my model, and that's the output. And here you can see that the output is exactly the same as the output from this blog post. So the output from GPT-J 6B after fine tuning. So basically, to summarize, you can train a model from scratch, or you can apply some fine-tune techniques to your model. And if you wanted to learn more which models you can, for example, let me show something to you. If you wanted to find out what the models that what models that allow you to fine tuning, this is really straightforward, because you can go to the Sagemaker Studio, go to the home page like here, and if you look at the Jumpstart models, you're going to see that we have foundation models section, right? Like this is text generation. So for example, Fluent 5 extra large is fine tunable. The Alexa TM 20 billion is not fine tunable. The Open Llama is not. You can see that models like GPT-J 6 billion is fine tunable. Same thing with BloomZ and many others. So I'm going to pause for now, because that was pretty much I wanted to share. Just wanted to see if you guys happen to have any questions.
Andre, I think there are a couple questions in the chat. One about how many GPUs does GPT-J 6 billion requires?
I'm sorry, say that again.
How many GPUs does GPT-J 6B require?
There is not a requirement, because, for example, the model I showed you. So if you are talking about training from scratch, or you're just talking about serving it for inference?
Both, if possible. Fine tuning and for inference.
Yeah, if you look at this for fine tuning, you may use for example. Let me go back to this sample over here. In this case, I use the G5 24 extra large, right? But that doesn't necessarily mean that I need a big instance like that. I can use some of the techniques that I talking about, like model parallelism, and instead of using a single GPU, I can a single instance with a single GPU or multiple GPUs. I can have multiple instances with multiple GPU with smaller GPUs. So there is no there are some limits, but we don't need to use a large one like this, right?
Okay, so as long as the model fits in memory, if I'm not
exactly, you got it. So if you use some of the techniques I spoken about with model parallelism and tensor parallelism with deep speed, you are able to split the model across different instances with multiple GPUs. Of course, you're going to need to handle with things like additional overhead for the network communication, right? But you don't need to think about that, because the Sagemaker parallelism library handles everything under covers for you. So basically, you need to set up things as I just showed you, like you need to set up, for example, for the deep speed, the parallel degree, the task you are doing, the type of the model, and things like that. So you don't need to implement everything from scratch, but basically leverage the documentation. And if we look at this documentation over here, so you're going to find that you can use a Sagemaker distributed model parallel training with tensor parallelism. And then you're going to find all the parameters you need to set up for to be able to do this additional training in case you wanted to train in one additional model from scratch. But this is one example on how to run a training job with tensor parallelism. which is a different thing than whole chain model. But this is a great source of documentation, as well as it provides some distributed training notebook examples, right? Which is a great source for those of you that wanted to learn more.
Nice, thank you. I think Osan has a question as well.
Yeah, I think another question Osan had was, do we support Clara or PAFT? If we have a notebook example for them.
Yeah, if you support 8-bit 4-bit training, and I think QLoRa is 4-bit training. So do you support those?
Yes, we do. Yes, we do.
You have sample notebooks that we can take a look and maybe we can practice.
Oh, absolutely. So do you have any specific use case, or basically you are just experimenting with this?
Yeah, the idea is, training with 16-bit is pretty expensive. So if we can deploy an open source model, and it may be GPT-4J, or maybe you heard the Falcon is very, has promising results. So I was thinking to deploy the Falcon model and fine tune with QLoRa, and so I was gonna try that. So if you have, if this is possible, so
Yeah, this is possible to be done. I can provide you with a few links on how to use LoRa with some of these models, and definitely you can give it a try.
yeah, thank you so much.
So
Right.
I have also compiled a few resources and code examples to train a host large language models. And on top of that, of course, I'm going to be sharing this slide deck, some useful resources for fine tuning and domain adaptation, as well as some RAG examples and additional RAG examples using OpenSearch and Kendra. I know this was not the topic of this session, but I know you guys have seen this throughout the days when all my colleagues were presenting.
Yeah, for all the slide decks here, we'll be sharing that. I will send out an email after this with all the slide decks. And for the earlier, the lab 1, you still have